The American power grid has almost no spare parts for the machines that matter most. Roughly 8,000 large power transformers carry electricity across the country. Each one takes up to 4 years to replace. A classified federal study concluded that attacks on just 9 key substations could black out the entire nation. On April 16, 2013, someone with a rifle decided to test that. At 4:43 a.m. on April 16, 2013, gunfire broke the silence at the Metcalf transmission substation near San Jose. Shooters opened with high-powered rifles, shattering the fence and slamming bullets into the metal housings of massive transformers. Over the next 19 minutes, 150 rounds tore through the site. 3 fiber optic cables were severed with hand tools, silencing emergency calls and disabling communications. By the time the attackers slipped away, 17 of the 18 500 kilovolt transformers were punctured. Bushings ruptured, releasing 52,000 gallons of dielectric oil onto the concrete pad. The lone undamaged unit had been isolated before the shooting began. First responders arrived minutes after the last shot. There were no suspects, no vehicles, no faces on the surveillance footage, just distant flashes and the sound of metal under fire. The FBI classified the incident as vandalism. John Wellinghoff, then chairman of FERC, called it the most significant domestic terrorism incident against the U.S. grid in American history. PG&E's Mark Johnson described the attack as a dress rehearsal. The grid survived, but the breach exposed how little stood between a rifle and the machines that keep the lights on. A large power transformer is not a generic piece of hardware. These machines are the backbone of the transmission grid, each one engineered for a specific site and electrical profile. According to the Department of Energy, any unit rated at 60 megavolt amperes or higher qualifies. Most weigh between 150 and 400 tons and stand several meters tall, with custom windings and bushings shaped by the demands of their substation. No two are interchangeable. Even a small difference in impedance or cooling configuration can make a replacement incompatible with the surrounding network. Standards from IEC and IEEE set minimum requirements for insulation, voltage class, and safety, but the real-world result is a bespoke device, locked to its original foundation and grid connection. The core is built from grain-oriented steel, the windings from copper or aluminum, all sealed inside a tank holding thousands of gallons of insulating oil. Every detail from the tap changer to the terminal arrangement is specified in advance. When one of these transformers is destroyed, there is no off-the-shelf substitute. The process of building and installing a new unit begins from scratch, measured in years, not weeks. Damage to a single transformer is not a localized inconvenience. It is a national supply problem with no easy fix. A large power transformer cannot be replaced with a spare pulled from a warehouse. Each unit is built to order, engineered for its substation's voltage, impedance, and physical layout. The manufacturing process is slow by design. Grain-oriented steel for the core must be sourced and cut, copper windings shaped to specification, and tanks welded and sealed. Factory testing alone can take weeks, as each transformer undergoes short-circuit, thermal, and impulse trials. Global production is concentrated in a handful of facilities. Fewer than a dozen worldwide are capable of handling the largest units. In the United States, only 3 major plants remain, each operating at or near full capacity. Lead times for a new transformer now stretch to 36 to 48 months. Transport is another barrier. Moving a 300-ton unit requires a Schnabel railcar, a specialized vehicle of which only about 30 exist in North America. Routing a transformer across the country means negotiating bridge limits, track clearances, and state permits. Transport often proceeds at a crawl, and sometimes crews wait weeks for a single crossing. The result is a system where damage to one machine can mean years without a replacement, and no practical way to stockpile spares. Pacific Gas and Electric responded to the Metcalfe attack by announcing a $15 million security upgrade. The company's internal memo outlined new barriers, additional cameras, and revised emergency protocols. State regulators at the California Public Utilities Commission opened an audit, issuing directives but leaving the specifics to PG&E's discretion. Mark Johnson, PG&E's transmission vice president, described the incident as a dress rehearsal. His words reflected a corporate understanding that the attack was not random, but a calculated test of the grid's defenses. The upgrades, though immediate, were incremental. Fencing was reinforced, lights were added, and patrols increased. The underlying architecture of risk remained unchanged. Johnson's memo acknowledged the event as unprecedented, but the response targeted symptoms, not causes. The $15 million spent, significant on paper, was a fraction of the cost of a single large transformer. The scale of the threat, measured against the scale of the remedy, revealed the gap between institutional response and systemic vulnerability. The grid's core weakness, custom machines with no spare parts, persisted beneath the surface improvements. In the aftermath of Metcalfe, federal officials moved quietly. A classified analysis by the Federal Energy Regulatory Commission and the Department of Energy, completed in June 2013, modeled the grid's weak points. The study found that disabling just 9 key substations out of more than 50,000 could trigger a blackout, stretching across the continent, with outages lasting weeks. The exact locations remained secret, and the full report was withheld under national security exemptions. Even Freedom of Information Act requests returned only blacked-out pages, confirming the study's existence, but nothing more. The Wall Street Journal later quoted a Federal Energy Regulatory Commission official who said that a handful of substations, 9 in total, are single points of failure. Congressional testimony from John Wellinghoff echoed the risk, saying that there are ways that a very few number of actors with very rudimentary equipment could take down large portions of our grid. No list of sites, no public map, only the knowledge that the system's survival depends on a handful of unremarkable yards, guarded by chain link and discretion. The threat is documented, the vulnerability acknowledged, but the details remain locked away. On December 3rd, 2022, rifle shots shattered the quiet in Moore County, North Carolina. 2 substations, both owned by Duke Energy and classified as low impact under federal standards, were hit in rapid succession. The attackers targeted transformer bushings, disabling critical equipment and plunging nearly 45,000 residents into darkness. Temperatures dropped below freezing as power stayed out for up to 5 days. Shelters filled. Emergency services ran on backup generators. In one home, an 87-year-old woman died after her oxygen concentrator failed. Law enforcement arrived within minutes, but the shooters vanished without a trace. No suspects, no motive, no arrests. Official statements confirmed the sites had only basic perimeter fencing. Federal rules did not require hardening or armed patrols. The outage did not trigger a mandatory national investigation. For Moore County, the consequences were immediate and personal. For the grid, the event confirmed what Metcalfe had already revealed. The threat is not theoretical. The same tactics, rifle fire, rapid escape, and minimal technology can still disable the backbone of the system. The warnings were not hypothetical. The cost was measured in cold nights, lost livelihoods, and a single, irreplaceable life. Roughly 8,000 large power transformers anchor the United States transmission grid. Nearly half of these units were installed before 2000, and they are operating well past their intended lifespan. Each transformer is a custom build, engineered for a single location, with no interchangeable spares. The Department of Energy reports that more than 80% of these machines have historically been sourced from overseas suppliers. Only 3 domestic plants remain, all running at capacity. Lead times for a new transformer now extend to 4 years. There is no national stockpile. When one of these aging units fails, by accident or attack, utilities confront a supply chain stretched thin, with no margin for error. The system's fragility is not theoretical. A single destroyed transformer can mean months or years of waiting in the dark. Electricity demand in the United States is rising at a pace not seen in decades. AI data centers now draw as much power as entire cities, their servers running around the clock. Electric vehicle charging stations multiply along highways, while homes and businesses convert to electric heating. Since 2019, generator step-up transformer orders have surged by 274%. Substation transformer demand has more than doubled. These new loads arrive on a grid already stretched thin, its core machines aging and irreplaceable. Every new megawatt compounds the risk. The system's original safety margin has evaporated. There is no national reserve of large transformers, no plan for rapid replacement. In 2013, John Wellinghoff warned Congress that there are ways that a very few number of actors with very rudimentary equipment could take down large portions of our grid. That warning remains unheeded. The grid grows larger, older, and more exposed. The danger is not hypothetical. It is waiting. Mark Johnson called Metcalfe a dress rehearsal. The FBI labeled it vandalism. John Wellinghoff called it the most significant domestic terrorism incident ever against the U.S. grid. Today, the grid's spine remains exposed, with 9 substations and 4 years to replace. Vulnerability is not theoretical. It is operational. Decide what that means.